Hello everyone, in this video we're going to talk about discrete probability theory. The first definition I want to give you is called the probability functions. So a probability function assigns a probability to each possible outcome, where each probability is between 0 and 1. And the probabilities of all possible outcomes add up to 1. So in this definitions, we have some notations to illustrate this. So a probability function is denoted as P, and it's assign a probability to each possible outcome. So a probability we're talking about in this case is going to be P of X, for X is a possible outcome. Now each probability is between 0 and 1, and we see this in the last video already. So P of X is between 0 and 1. Now for the second point, the probability of all possible outcomes add up to 1. So that is if you have the probability of the first event plus probability of the second outcome, so on and so forth, plus the probability of the end event. They add up together and that is equal to 1. So the first rule that we're going to cover is addition rule of probability. So that is given two possible outcomes, A and B, we're going to get the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. In terms of notations, we can write P of A union with B equal to the probability of A plus the probability of B minus the probability of A intersect with B. In this case, the intersection between A and B is not going to be an empty set. All right. So let's consider the following example to illustrate the formula we just wrote down. So the example is, what is the probability of pulling a heart or a king in the standard deck of cards? So there are two possible outcomes here, that is either a heart or a king. So I let A be the event of pulling a heart, and B is the event of pulling a king. So to calculate the probability of pulling a heart or a king, what I write first is want to find the probability of a heart or a king. And this is equal to the probability of pulling a heart plus the probability of pulling a king minus the probability of pulling a heart and king. So this means that I want to know what is the probability of the card that I pull is a king of hearts. All right. In terms of notations, because we already let A to be an event of pulling a heart and B is the event of pulling a king, so we can write this particular equations in terms of notation as follows. So P of A union with B equal to the probability of A plus the probability of B minus the probability of A intersect with B. So what is the probability of A? So what is the probability of getting a heart? So there are 4 suits in a standard deck of cards: spade, club, diamond, and heart. And for each suit, you have 13 cards. So the probability of getting a heart is going to be 13 divided by 52. So the numerator is going to be the number of desirable outcomes of getting a heart, right? And the denominator is going to be the total number, is the number of total possible outcomes. In this case, the standard deck of cards have 52 cards. So the probability of getting a heart is 13 out of 52. Plus the probability of B, or the probability of getting a king. There are 4 kings in the deck of cards. So therefore you get 4 out of 52. And this probability is going to be the probability of getting the king of hearts. So there is only one king of hearts in the entire deck of cards. Therefore, the probability of this is going to be 1 out of 52. Because they have the same denominator, we're going to do 13 plus 4 minus 1 divided by 52, or it's going to be 16 over 52. And you can simplify this to get 4 out of 13. Or this is approximately equal to 0.31 or 31%. So there is 31% chance of pulling a heart or a king. Now let's move on to another example. We want to know what is the probability of getting an even number or a number greater than 4 from rolling a die once. So there are two possible outcomes as well. The first one is getting an even number, and you want to let A to be an event of getting an even number. So the possibility is going to be 2, 4, and 6. So the cardinality of A is going to be equal to 3. And then if you let B to be an event of getting a number greater than 4, the possibility is going to be 5 and 6. And therefore the cardinality of B is going to be equal to 2. Now, in calculating the probability of getting an even number or a number greater than 4 from rolling a die once, what you're going to get is the probability of A union with B equal to the probability of A plus the probability of B minus the probability of A intersect with B. And again, when you're calculating a probability, you want to find the fractions of the number of desirable outcomes divided by the number of total possible outcomes. So in this case, for the probability of A, that is the probability of getting even numbers, is going to be 3 over 6. For 3 is the number of desirable outcomes, or the cardinality of A in this case, and 6 is going to be the number of the total possible outcome, or in this case, the cardinality of the symbol space is going to be 6. And for the probability of B, you have the cardinality of B, or the number of desirable outcomes, going to be 2, and the number of total possible outcomes, or the cardinality of S, is going to be 6. And what about the probability of A intersect with B? That means what is the probability of an even number that is greater than 4? What is the desirable outcome here? So desirable outcome in this case of getting an even number that is greater than 4, there's just one possibility, which is 6 in this case. So A intersect with B means the even number that is greater than 4. And there is only one possibility, which is the element 6. So the probability of that happening is 1 out of 6 chances. Therefore, you're going to get 3 plus 2 minus 1 divided by 6. And you're going to get 4 over 6, or 2 over 3. Use a calculator and you get this approximately equal to 0.67 or 67% chance of that happening. So you conclude that there is 67% chance of rolling an even number or a number greater than 4. Now what happened when the intersection between A and B is equal to the empty set? In that case, we're going to call them mutually exclusive events. So if A and B are mutually exclusive, then the probability of A union with B is equal to the probability of A plus the probability of B, and that's it. Right? So the two events are mutually exclusive if A intersects with B equal to the empty set. In this case, A and B are disjoint. So let's consider the following example to illustrate the point here. So we want to know what is the probability of rolling a 1 or a 5 from a 6-sided die. Because the event of getting a 1 has nothing to do with an event of getting a 5. So A and B are mutually exclusive. So in this case, A is an event of getting a 1. So there is only one possibility of that happening. And therefore, the cardinality of A is going to be equal to 1. And B is an event of getting a 5. So there's only one possibility that is happening. Therefore, the cardinality of B is also equal to 1. And again, the event of getting a 1 has nothing to do with the event of getting a 5. So A and B are mutually exclusive. Thus, when we want to calculate the probability of rolling a 1 or a 5, we're going to get probability of A union with B is equal to the probability of A plus the probability of B. The probability of A is going to be 1 over 6, and the probability of B is also 1 over 6. Therefore, you get 2 over 6, or 1/3. And this is approximately equal to 0.33 or 33%. So you conclude that there is 33% chance of rolling a 1 or a 5. Now the property I want to give you is called complementary events. So the probability of the complementary event is going to be equal to 1 minus the probability of the event itself. So in this case, E is going to be an event of a sample space S. And E bar represents the event that E does not occur. So now what is the probability of not getting 4 of a kind in a standard 5-card poker hand? So we can let A to be an event of getting 4 of a kind. And therefore the event of not getting 4 of a kind is going to be A bar. So calculating the probability of not getting 4 of a kind is going to be P of A bar equal to 1 minus P of A. So to get the value of the probability of A bar, what you need to do is actually calculating the probability of A. So that is the So what is the probability of getting 4 of a kind hand out of the standard 5-card poker hand? So similar to other example, well, when we try to calculate the probability, you want to know what is the number of desirable outcomes and what is the number of the total possible outcomes. So for desirable outcomes, so the number of desirable outcomes. So you know that there are 4 cards of each kind and there are 13 kinds. That is, you have Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. So this is going to be 13 times the number of possibility for the last card in the hand, which is 48. So that means you take 52 minus the 4 cards of the same kind, you get 48 left in the deck of cards. So the number of desirable outcomes going to be 13 times 48 is equal to 624 desirable outcomes. So the 13 that you see in the calculation is not about counting the 4 cards themselves. What we did is that it is counting the 13 possible ranks that you have in the deck of cards. That is the Ace, the 2, 3, 4, 5, 6, 7, 8, 9, 10, the Jack, Queen, and King. And that could make up the 4 of a kind. And now once the value or the rank is chosen, the 4 cards are determined automatically. Hence the result of 13. Another way to think about this number 13 is that because there are 13 ranks or 13 different kinds in the deck of cards, you just choose one of them and work with it. So you can use combinations of 13, 1. And if you do the calculations correctly, the result should give you 13 as well. And for the number of total possible outcomes of the 5-card hand is going to be the combinations of 52, 5, because you can choose randomly 5 different cards in a deck of 52 cards. Therefore, the probability of A is going to be 624 divided by the combinations of 52, 5. So we're going to do a little bit of work on the combinations of 52, 5. So the combinations of 52, 5 is equal to 52 factorial divided by 5 factorial times 52 minus 5 factorial. is going to be 52 factorial divided by 5 factorial times 47 factorial is going to be 2,598,960. So you're going to put this number into the denominator of the probability of A. So you're going to get 624 divided by 2,598,960. So that is the probability of getting a 4 of a kind hand. Now, what is the probability of not getting 4 of a kind hand in the standard 5-card poker hand? So you want to calculate P of A bar equal to 1 minus P of A is equal to 1 minus 624 divided by, and find a common denominator, and you're going to get 960 minus 624 and you're going to get 2,598,336. And if you use a calculator, you're going to get, so it's going to be around 0.99976. So the chance of getting 4 of a kind in a 5-card poker hand is going to be very slim. The probability of not getting 4 of a kind is almost equal to 1. Alright, so that's it for me. That's it for discrete probability. We're going to move on to another concept called conditional probability in the next video.